Hello and welcome. Today, we're exploring the fascinating world of extended reality, or XR. This includes virtual reality, augmented reality, and mixed reality, technologies rapidly changing how we interact with digital information and simulated environments. We'll focus on the cognitive neuroscience of XR, how our brains adapt and what effects these immersive experiences have on us. Our brains exhibit remarkable adaptability, a phenomenon known as neuroplasticity. Engaging with demanding tasks in XR can actually strengthen neural connections. This is particularly promising for aging populations and individuals recovering from brain injuries. XR offers controlled, enriched environments for multisensory stimulation. This can help counteract the negative effects of inactivity. Studies show VR interventions can induce significant neuroplastic changes in brain regions like the hippocampus and prefrontal cortex, leading to improved memory, spatial navigation, and executive functions. Now, let's consider cognitive load. This theory helps us understand how we process information in XR. There's intrinsic load from task difficulty, extraneous load from how information is presented, and germane load related to learning. While XR can offer rich information benefiting memory, poorly designed experiences can increase extraneous load, negatively impacting information processing. Researchers are working on optimizing XR design to manage this, perhaps by dynamically adjusting difficulty based on real-time neural data. So, what are the effects on users? XR's immersive nature significantly impacts cognition and emotion. It enhances learning and skill acquisition. Active participation in realistic simulations promotes deeper understanding. XR can also improve attention and spatial cognition, with eye-tracking technology even allowing for gaze-based interaction. Memory can get a boost too, especially for older adults, as XR simulates real-world scenarios for active interaction. Furthermore, XR's immersion can foster strong emotional connections and empathy, and is often perceived as more engaging and motivating than traditional tasks, which is great for education and therapy. The principles of XR's cognitive neuroscience are already being applied clinically. XR provides realistic tools for assessing cognitive functions like memory and attention. In rehabilitation, it offers a safe space for patients recovering from brain injury, stroke, or those with neurodevelopmental disorders like autism spectrum disorder to practice skills. VR-based programs have shown promise in improving motor function and social cognition. XR is also used in mental health for exposure therapy for PTSD and phobias, and even in pain management. However, there are challenges. Prolonged XR use can lead to cybersickness, nausea and dizziness, plus eye strain and discomfort. Designing for usability and accessibility for diverse populations remains crucial. Poorly designed XR can also lead to cognitive overload. We still need more research on the long-term psychological and neurological impacts, especially for children. And, of course, ethical concerns around data privacy and potential psychological manipulation are paramount as XR becomes more widespread. Looking ahead, future research will likely focus on optimizing XR with technologies like EEG and haptic feedback for more personalized experiences. Understanding how our brains adapt and exploring XR's therapeutic potential will continue to be key. Collaboration between neuroscience, cognitive science, and XR developers is vital to harness XR's benefits safely and effectively. Thanks for listening.